Microprocessors made of silicon are the basis of our society. They're used in televisions, radios, video games, cars, aircraft, washing machines, central heating systems, and of course all of our computers. They're made in highly automated fabrication lines, and hundreds of microprocessors are made on each silicon wafer. If a wafer breaks during the production process, it is catastrophic. It can cost 2 or 3 days production to clean it out. It's a rare event, but nevertheless it costs several millions of euros every year per fabrication line. The important defects are the tiny cracks around the edge of the wafer. The silicon manufacturers asked us to develop a way of predicting which wafers would break in production machines.
So Jordan Valley had a great product for analysing and detecting defects in wafers. However, they weren't sure how those defects affected the manufacturing process.
The BitScan product use X-ray, and we do X-ray diffraction imaging with this equipment. With that, we are doing pictures of the inside of the wafers and measuring the defects that are on those silicon wafers. The BitScan basically is showing a lot of defects in wafers, but it doesn't tell you which one are important and especially which one are critical to the semiconductor industry.
The role of CIT in the project is generate the control damage within wafers, model the stresses around them, and then trying to break them within the rapid thermal annealing furnace.
We are creating some samples to deliver to the rest of the partners here. We are using the indentation technique to create some distortion and some fracture on the material. You have a tip. Essentially, you apply a load on the material, so you deform the material, creating an impression and also some cracks and some distortion of the material.
In the SIDAM project, we use the anchor and diamond synchrotron radiation sources. These sources provide intense beams of X-rays which we use to study the cracks in the silicon wafers.
Anchor is a strongly technology-oriented synchrotron user facility. We can understand it as operating a big carousel of electrons which are accelerated to the speed of light and now turning in this carousel, and if they change directions, then they are so happy to do that they radiate. And what's important is they radiate not normal radiation, they radiate radiation up to the hard X-ray range. And those X-ray photons are highly brilliant and highly collimated X-ray photons, so going in a straight direction in the way as a laser is doing. With those X-rays we can look deep into the structure and the dynamics of the materials.
This is first of all a very big goniometer where we can handle wafers up to 300 millimeter diameter, but also tiny samples. And for the smaller samples we have a heating equipment where we can go up maybe 1100, 1200 degrees Celsius for the high temperature in situ experiments. We checked again the crack formation in samples before a heating experiment. Then we inserted the heater and we looked in situ up to 1100 degrees how a crack was formed and propagated through a wafer, and a lot of thermal slip bands were also formed, and the interaction of these dislocations and slip bands was also documented in real-time movies.
We use both the anchor and diamond facilities because they have different strengths in relation to our project. At Anchor, we have facilities to do experiments in situ, whereas the diamond light source has an extremely small and brilliant source. This enables us to fully utilize facilities across Europe.
So within this project, we have used finite element modeling in two ways. One was to calculate the stresses around cracks and see how a crack initiates around an indentation, how it evolves. And a second big work that has been done with finite elements deal with the furnace. So we were modeling the furnace, we were modeling the wafer inside the furnace and the temperatures within the wafer during a heat treatment. So from these temperatures, we could calculate the forces that appear within the wafer during the heat treatment. And we can see whether a defect, a crack, will grow or not during the treatment. So like this, we are able to predict fracture. But we have to be careful because we have always to check models against experiments.
The contribution that we make to the SIDAM project is twofold. We assist with the X-ray diffraction imaging experiments, both performing the experiments in the synchrotron and with a lot of post-processing where we do three-dimensional rendering of that data. So essentially we produce really fancy 3D images, very much like your X-ray CAT scan data. But the other thing we do right here in one of our laboratories in DCU is we carry out what are called micro-Raman spectroscopy measurements. We can use our data to back up the data of our colleagues over at the synchrotron sources, because they're doing direct, in a sense, imaging of what's going on inside our silicon. Our silicon, of course, has been deliberately damaged. We ask the question, is that region around these damaged indents under compression or tension? Raman spectroscopists like myself go, aha, we can answer that question for you, and we can do it non-destructively. We can measure that stress state right up near the surface of the sample or quite deep down into the sample.
By the end of this run, we will have studied a large number of wafers with cracks arising from the handling damage. These will now be taken back to San Sebastian in Spain, where they will be rapidly thermally annealed, and we will see how many of the cracks propagate when they are thermally processed in this way.
Our business, in fact, is to break things. And we are very happy when we break things, and the goal of breaking things is to avoid them breaking in the real world. So that's what we do.
Nothing is so practical as a good theory that has been tested by experiment. So the final stage of the testing is to introduce a crack that we believe will be dangerous, subject it to a rapid thermal anneal and see if it breaks. The modelling of the furnace itself shows that the outside of the wafer heats and cools more rapidly than the inside. And cracks can form in the red area, starting from the edge and running through to the boundary between the red and blue area. So we can now predict from the original X-ray image whether a wafer is likely to shatter during a certain thermal treatment.
It's important to Intel to be able to maintain the pace of Moore's law, and because of that we need to bring in new materials into our manufacturing processes. We need to bring in new process technologies, we need to bring in new ways of measuring what we do in the factory. Intel doesn't have all of the capability itself. It needs to collaborate with research organisations around the world, academic institutions, and across Europe there are some great people that are able to help us in this quest. Therefore, working in Europe enables Intel to strike relationships with some really good technologists and people who are the best at what they do in the business.
The main outcome of the project is that we've developed the QCRT instrument, which performs a subset of the X-ray diffraction imaging measurements that the bead scan will perform.
The tool that will identify the defects that are required, and also the software to automate this process.
And the special feature of this project is the industrial advisory panel that we've assembled from prominent semiconductor industries in Europe. And these senior scientists meet every year in London in order to steer our project, to hear what we're doing, what we're planning to do, to give their advice, and of course to take the results back to their own companies to learn how to put our ideas and discoveries into production.
For us as a foundry, it's of high importance to control the quality of the wafers, both incoming wafers, wafers in production, and also wafers we yield to customers.
One of the very important things about a European research program is communicating the results to other scientists in universities and in industry and to the community at large.
The nanotechnology knowledge transfer network is a network which actually does a lot of dissemination of information. So one of the dissemination methods for this particular project would be via our particular network.
From my point of view, I'm gaining a lot of experience and a lot of getting to know how to work with, within a cooperative.
The SIDAM project is incredibly useful for my education and my formation because it is training me both from an experimental and from the theoretical point of view.
Well, it has given me experience in the modeling world, and also now I've got another point of view of material science. It's much more broader.
You couldn't do the same if you were working alone in your own lab.
I think that probably 10 different nationalities are represented in all SIDAM meetings.
It's nice to work with people from different countries because you get to know how they work and you learn about new different techniques.
You get to know the network.
And also on a personal level, I mean, I enjoy getting the work done. I enjoy doing things that nobody else has done and solving problems that people have come up with and they have not got a solution for, they haven't been able to find a solution for, and we're going and finding that solution.
This European collaboration has solved an important industrial problem, and it will help to keep these vital products affordable in the future.